Hello and welcome to this new video. In this video, I'm going to solve the exercises of chapter 3. Okay, so exercise 1, show that the equation 2 to the power x plus 3 to the power x equals 7 to the power x has a solution between 1/2 and 1. Okay, this is very easy. This is a consequence of the intermediate value theorem. So let f of x be the difference between the two sides. It's a continuous function on R. And if you evaluate f at 1/2, you will get radical 2 plus radical 3 minus radical 7. And this is something, of course, you can compute it with the calculator, but even without a calculator, you may check that this is something positive. Okay? Because f of 1/2 positive is equivalent to saying that radical 2 plus radical 3 is bigger than radical 7. And when you square, you get 5 plus 2 radical 6 bigger than 7, and when you subtract 5, you get 2 radical 6. 2 radical 6 is bigger than 2, so it's true. Okay, so even without a computer, you can check that f of 1/2 is positive. And on the other hand, f of 1 is negative. So by the intermediate value theorem, f vanishes at some point between 1/2 and 1. And that's it. Next exercise, also about the intermediate value theorem. So we have a polynomial, x5 minus 3, x minus 2, and we want to show that it has a root between 1 and 2. So evaluate p at 1. So both are continuous, actually, p and f. So p at 1 is negative and p of 2 is positive. Therefore, there's a root. For f, we have f of 0 is negative and f of 1 is positive. So once again, we can apply the intermediate value theorem because f is continuous. Now, for the last question, we do the difference and we evaluate h, the difference at 0. It's negative, and h of 2 is positive. So once again, by the intermediate value theorem, h vanishes at some point c between 0 and 2, and therefore, at this point, p of c equal f of c. Okay. So this is straightforward, actually. Next result, show that every polynomial of odd degree has at least one real root. Okay, so we write the polynomial as usual, so a0 plus a1x plus etc. up to a2p plus 1 x2p plus 1. And if it's a polynomial of degree 2p plus 1 odd, it means that the leading coefficient, this is the leading coefficient, is not 0. So it's either positive or negative. And actually, it's enough to assume that it's positive. If it's positive, then when you factor the polynomial by x2p plus 1, we get this result. Okay, so all these terms which are divided by a power of x, when x tends to infinity, they vanish. So the limit of p of x is plus infinity at plus infinity. So, okay, and at minus infinity, it's minus infinity, because you are assuming that the leading coefficient is positive. Okay, so in particular, if p of x tends to infinity at infinity, it means that it's positive at least for some value, x1. And if it tends to minus infinity at minus infinity, then it's negative for some value of x2. So by the intermediate value theorem, p vanishes at some point between x1 and x2, or x2 and x1. Okay. And if the leading coefficient is negative, okay, we can do a similar study, but we can deduce if the leading coefficient is negative, then we consider the polynomial minus p. And then the leading coefficient of minus p will be positive. And so according to what we said, minus p has a root, and therefore p has a root. Okay? So this is a consequence of the intermediate value theorem. Next result, also an application of the intermediate value theorem. You have to solve the equation x plus ln x equal 3. We have to show that there is one and only one solution in the interval 1e. So we take the difference, we call it f for x positive. So we have a continuous function, and at 1 it's negative, at 2 it's positive, and therefore it must vanish at some point between 1 and e. This is the intermediate value theorem. Now, why is it unique? Well, because the function is strictly increasing, so it's injective. How do you see that it's strictly increasing? Well, you can compute the derivative if you like. You get a positive result, so f is strictly increasing and therefore injective. So the solution is unique. Or you can say that this is increasing, the sum is increasing strictly, so it's injective, okay, as you wish. So this is easy. Okay, now a difficult question, okay, it's of theoretical nature. If f is continuous from R to R and vanishes at infinity and minus infinity, then f is bounded and uniformly continuous. Okay, so let us first tackle the problem of boundedness. How do we know that f is bounded? Okay, we go back to the definition of limit at infinity. What does it mean to say that limit at as absolute value of x tends to infinity of f of x is 0? It means that f in absolute value can be made less than any positive number I like if x in absolute value is large enough. This is the definition actually of a limit at infinity. So when x is large enough, f of x can be made less than any number I like. Okay? And so in particular, if I take epsilon equal 1, so note in general the r depends on epsilon. So take epsilon equal 1 in particular. So you will have a number r such that f of x is less than 1 for x outside the interval minus r. Okay. And now if you consider f on the compact set minus r, we know that a continuous function is bounded on a compact set, right? So we have two things. So we split the real number, the real line, into two parts, the interval minus r and the outside of this interval. On the interval, f is bounded, so let us say by a constant m that depends on r. So in particular, f of x is less than m plus 1. And outside the interval, f is less than 1, so it's also less than m plus 1. So for all x in R, if we combine these two conditions, f is less than m plus 1 in absolute value for every x in R. Okay. So the idea is very easy. So it's bounded inside the interval and it's bounded outside the interval. So therefore it's bounded on R. Okay, on the whole line. Okay, so this is not so difficult. You should be able to do such reasoning. Now, the question of uniform continuity is a little bit trickier, okay? So once again, we go back to the definition of limit at infinity. So we have this condition. And okay, and now once again, I fixed the epsilon, okay? And I split the real line into two parts once again, the interval minus r and outside the interval. Now, on the compact interval minus r, f is continuous and therefore uniformly continuous by the Heine-Borel theorem. Okay? So therefore, there exists a delta that depends on epsilon and r such that this condition holds. This is the condition of uniform continuity of f on the interval minus r. Okay? This is what we have. But this is not what we want to prove. We want to prove this for every xy, actually, in the real line, not just on the interval minus r. Okay. But this is the first step. Okay. Now, okay, take the same delta, actually. We'll show that this delta works for every xy. Okay. So we distinguish between four cases now. If we take any two arbitrary numbers, x and y, whose distance is less than delta, we have four cases. Either both are in between minus r and r, or both are outside, or one is inside, the other is outside. So same thing. Okay, so if now both x and y are in the compact interval, by the condition that we just proved, then the distance between their images is less than epsilon. This is condition 2. So this is not a problem. Now, if both are outside minus RR, so either both are bigger or smaller, or yeah, one is less than, okay, we cannot have x less than minus r, y bigger than r, because their difference is less than delta. But at any rate, if they are outside this interval, I know by condition 1 that f of x is less than epsilon in absolute value, and f of y, same thing, is less than epsilon. So by the triangle inequality, their distance is less than 2 epsilon. Okay, now the third case, x is between minus and r, and y is bigger than r. Okay, so r is between x and y, so x less than r, r less than y. Okay, so r is between x and y, so the points x, r, y are in this order. So in particular, the distance between x and r is less than delta, because the distance between x and y is less than delta. Okay, just draw a picture. Okay, so x, r, y. And so once again, I apply the triangle inequality, so I add and subtract f of r. F of x minus f of r is less than epsilon y, because x and r are by step 1, actually, by case 1. Okay, and f of r minus f of y, I cannot apply 1 actually, but I apply step 2 actually, case 2. So the first term here is less than epsilon. The second term by the triangle inequality is less than f of r in absolute value plus f of y. And each of these terms is less than epsilon. So we get that the distance is less than 3 epsilon actually. Okay, case 4 is just similar to case 3. X is, so here we have y less than minus r less than x. Okay, so it's completely similar. Okay, these are the whole cases. Now, of course, you may say, well, what if y is between minus r and x is outside? It's the same thing, just you relabel. Okay, so call x the one which is bounded, the variable which is between minus r and r. Okay, so these 4 cases cover all the possibilities. And therefore, in all cases, whenever we have x and y satisfying x minus y less than delta, we have f of x minus f of y is less than 3 epsilon. So what we proved is that, but epsilon was arbitrary, okay? And this is just the uniform continuity condition. Now, if you get 3 epsilon, 5 epsilon, or 100 epsilon, it's the same thing, because if epsilon is arbitrary, then 3 epsilon is also arbitrary, okay? Otherwise, you may take here, if you like, epsilon over 3 on here, and here epsilon over 3, and then you get exactly epsilon. But this is not at all necessary, okay? If you get 5 epsilon or 100 epsilon, and epsilon is arbitrary, so just proved what you want to do. So we proved that actually what? That for every epsilon, there exists delta that depends only on epsilon, such that if x minus y is less than delta, then the distance between the images is less than 3 epsilon. Okay, and this is just uniform continuity, not just continuity. Okay, because the delta does not depend on x, it depends only on epsilon. Okay, it depends on r, but r depends on epsilon, so delta depends on epsilon. Okay, and that's it. Okay. Last exercise, also similar, but we have now a periodic and continuous function. We have to show that f is bounded and uniformly continuous. So once again, boundedness is, okay, this exercise is a little bit more difficult than the previous one, and I don't expect from you to be able to do it on your own, okay? But here's the, so, but you should be exposed at least, and at this, you should be exposed to the proof. Okay, so maybe next year or in the 3rd year you'll be able to do on your own such reasoning. Okay. Okay. So let t be the period of f. So f of x plus t is f of x. Since f is continuous on the compact set 0t, then by the extreme value theorem, f is bounded, right? So there exists a constant m such that f of x is less or equal than m for all x between 0 and t. Now, if we take, I will show now actually that m is an upper bound of absolute of f for every x in R, not just on t. And this is a consequence of periodicity. Okay, now if you take x in R and take n to be the floor function of x over t, and I will tell you why did I choose that in a moment. You'll understand why. If n is the floor function of x over t, it means that x over t is between n and n plus 1. And when I multiply by t, I get that x is between nt and n plus 1t. So x lies necessarily in an interval of length t. When I subtract nt, so it's a translation. So when I translate x, okay, so suppose that the interval 0t is here and x is here. By translation, I can make x be in the standard interval 0t, in the reference interval. Okay, so now x minus nt, the translate of x, is in the interval 0t, and therefore, according to what you said, f of x minus nt in absolute value is less than m. But since f is t periodic, then f of x minus nt is just f of x. This is the periodicity. So I proved that actually f of x is less than m, and x was arbitrary in R. Okay, and the constant m does not depend on x. Okay, it depends on t and f, of course. Okay. So this is the idea. So we do a translation to make, and this idea we shall use it in the next. So this proves the first point of boundedness. So f is bounded on the whole line, and intuitively this result should be clear, because take a periodic function like cosine or sine. Since the function repeats itself, it's bounded actually. Okay, but this is the rigorous proof that of boundedness of f on the whole line. Okay, now uniform continuity is a little bit trickier. Okay, so let epsilon be a given positive number, which is arbitrary. Now, on the compact interval 0t, f is uniformly continuous by the Heine-Borel theorem because it's continuous. So continuous on a compact set means uniformly continuous. Okay, so I write I can find a number delta that depends on epsilon and t, such that this condition holds. This is the condition of uniform continuity on the interval 0t. Okay. Now, of course, I may assume that delta is smaller than t, because I can delta, if this works for delta, it works for any smaller delta. So delta can be chosen as small as I wish, actually. And now this condition holds for 0t, but now by periodicity, it also works for x and y in t to t, because I just do a translation. If x and y are between t and to t, then x minus t and y minus t are here. So f of x minus t minus f of y minus t is less than epsilon, but by periodicity they are equal. So actually, by periodicity, this condition works on any interval of length t, right? Okay, so it works on 2t, 3t, anything you like. Okay, but I just need these two conditions that I call 3 and 4. Okay, and now I need to prove that this delta works for every x and y in R. Okay, so now call x, if you relabel them after relabeling, you can always assume that x is less than 1, because one of them is less than the other. Okay, if x equal y, it's not really, it's trivial actually. So assume that x is less than 1. So call x the smallest between the two numbers. Okay. Now, as in the first part, there exists an integer such that when I translate x by a multiple of t, I am in the interval 0t. Okay, so n is the floor function of x over t. Okay, now if you consider the number y minus nt, now y minus nt need not be in 0t, but so we have two cases now. If you consider this translate of y by the same number n. So here we have two cases. Either y minus nt is in this my reference interval 0t, or it's not. in the first, so suppose now that y minus nt is in the interval 0t. So what do we have? Both x minus nt and y minus nt are in the same interval 0t, and their difference is just x minus y, which is less than delta. So the distance between their images by periodicity is just the difference between f of the translates. And by condition 3, this is less than epsilon, because both these numbers, x minus nt and y minus nt, are in the interval 0t. Okay, if their difference, if the distance between them is less than delta, then the difference between their images is less than epsilon. Okay, so this concludes the first case. So f of x minus f of y is less than epsilon. Now, the second case, y minus t is not in the interval 0t. So what does this mean? It means that either y minus nt is negative or bigger than t. Now, it cannot be negative. Why? So we claim that actually y minus nt is necessarily in the interval t to t. Okay, so we have to rule out the possibility of being negative, of y minus t being negative. Okay, so first, so we have x less than y, and y minus x is less than delta. So y is less than x plus delta. Okay, this condition, if I put everything together, I get y less than x plus delta. So when I subtract nt, we get y minus nt is less than x minus nt plus delta. Okay, now x minus nt is less than t, okay, by definition of n. So x minus nt plus delta is less than t plus delta, and I chose delta to be less than t, so we get less than 2t. So the y minus nt is less than 2t. Okay, now why is it bigger than or equal than t? Because it cannot be negative, because y is bigger than x. So y minus nt is bigger than x minus nt, and x minus nt is positive. So the y minus nt is bigger or equal than 0. So it cannot be negative. So it's necessarily bigger than t because it does not belong to the interval 0t. Okay? So it's bigger or equal than t, and therefore we get the claim is proved. Y minus nt is between t and 2t, and now we are almost done. So this proves the claim. But now we have to. Okay, so what do we have now? We have x minus nt is less than t, and y minus nt is bigger than t. So these 3 points are in this order: x minus nt, t, and y minus nt. And the difference between y and x is less than delta and positive. Okay, now what do we have here? If x minus y if y minus x is less than delta, then x minus nt minus t is also less than delta, because this is in between. If the length of this interval is less than delta, then the difference between these two numbers is also less than delta. And similarly for the other two, because just plot x minus nt, t, y minus nt. So the distance between x minus nt and t is less than delta, and similarly for y minus nt and t. And now we just have to put everything together. If I consider f minus f of y, f of x minus f of y, by periodicity, f of x is equal to f of x minus nt, and f of y equal to f of y minus f minus nt. And now I just add and subtract f of t, and I apply the triangle inequality. Now, x minus nt and t are both in the same interval, which is 0t, and the distance between them is less than delta. So the distance between their images is less than epsilon. Now, t and y minus nt are both in the interval t to t, in this case, and their difference, the distance between them is less than delta. So the distance between their images is less than epsilon, and therefore I get f of x minus f of y is less than 2 epsilon. And that's it. So this proves that since epsilon was arbitrary and x and y were arbitrary, we just proved uniform continuity on R. And that's it. So this concludes the exercises. I admit that it's not trivial. So it took me some time to figure it out. I don't expect from you to be able to do it on your own, unless you are a genius. But you should be exposed to this kind of theoretical reasoning because it's really fundamental in analysis. Okay, so maybe next year or the year in third year or fourth year, when you gain enough mathematical maturity, you will be able to do such things on your own. But at this level, so don't worry. I will not ask you such a complicated thing in the exam unless I give you a hint. Okay, so that's it. So don't worry. And this concludes the exercise, this video about the exercise of chapter 3. In the next video, I'm going to start chapter 4. So thank you for your attention.